Hello, I'm here to talk to you about the Serge Modular Archive Instrument, or SMAI. My name is Ted Moore. I'm currently based in New Haven, Connecticut, and I made this in collaboration with Jean Brazeau, who currently lives in Vancouver, British Columbia. While we were building this together, he was studying at Simon Fraser University there, which will become relevant momentarily. So the Serge Modular Archive Instrument is a sample-based computer emulation of the vintage Serge Modular system that is housed at Simon Fraser University. We recorded around 50,000 one-second samples, which is about 14 hours of audio, for 4 different patches that we made on that vintage Serge Modular. And I say around 50,000 because we have recorded this for 4 different patches, and each one has a slightly different set of samples for reasons I'll explain later. With those 1-second samples, we did some audio analysis and statistical analysis on those audio analyses to end up with 357 different analysis values for each 1-second sample. We then make all of these samples available through a Skeuomorphic control that is modeled on the vintage Serge Modular design, and a 3-dimensional plot that one can mouse through and browse these different sound samples and hear them and play with them. We've recorded and analyzed 4 patches so far, and we're planning to add more as we have time to do more recording and analysis. The way that we would create this data set for each one of these 4 patches is we used a super collider script to provide control voltage outputs via the Expert Sleeper's ES3 module. Here we can see it's patched to 8 cables, but we actually just chose 4 different control parameters that were controlling particular parameters on this vintage Serge Modular. And then we programmatically stepped through all the possible parameter combinations for these voltage control parameters that we selected. For each control parameter, we had between 10 to 15 steps that we would step through, ranging between negative 10 volts and positive 10 volts, which is the output of the Expert Sleepers. Sometimes we would have closer to 10 or closer to 15, depending on what that parameter was and how important it was to have a more or less fine resolution. And also sometimes we adjusted the range to not be negative 10 to positive 10, but some range smaller than that, depending on what the parameter was. Perhaps it was an oscillator and it wasn't useful for us to sweep that oscillator way up above the range of human hearing, and so we wouldn't use that voltage range while we created this data set. So using 4 voltage controlled parameters on the Serge Modular, each having around 15 different discrete steps, that would be 15 to the power of 4, which is 50,625 different parameter combinations, so about 50,000. Once each one of these parameter combinations was sent to the Serge system, we recorded the audio for 1 second. We initially recorded this at 96 kilohertz and 24 bits, but because this ended up being a huge amount of data, for our actual analysis and playback, we chose to reduce this down to 44.1 and 16 bits. And of course, as we were recording all this audio, we were also logging the parameter positions, so what the actual 4 control voltage signals were set to, and also the audio start and stop positions, so later we could pair back which control parameters created which 1 second of audio. In order to do the audio analysis, we used the Skeuomorphic toolkit, and we selected to do these audio analyses, many spectral descriptors, pitch confidence, some loudness descriptors, and then 40 MFCC values, which is a total of 51 different audio analyses, counting the 40 MFCCs. The Skeuomorphic analysis objects will return for us a time series of these different audio analyses across the 1-second sound slice that we're analyzing. So for example, here the red line is spectral centroid, and we can see that in this 1 second of audio, there might be a variety of spectral centroids that change over time. In order to summarize each one of these analysis time series down to a smaller number of values, we decided to do a statistical analysis on the time series of each audio analysis for the sound slice. We used these 7 statistical summaries, all of which are available through Skeuomorphic, and this meant that for each sound slice, we ended up with 357 total analysis values per 1 second sound slice. We had 51 audio analyses and 7 statistical analyses for each one of those audio analyses, so we had 51 times 7 is 357 different values. The first way that a user might interact with these sound slices is through the Skeuomorphic interface. You can see here there are 4 highlighted knobs, showing which knobs a user can interact with and will change the sound in some way. As the user moves these knob positions are sent to a KD tree, which has been fit on the data set of parameter combinations to query what the nearest neighbor of these current parameters are, finding the sound slice that is associated with that parameter combination, and then playing back the sound slice. Here is the SMAI software loaded up with one of the patches that we recorded and analyzed. And I'll first draw your attention to the skeuomorph over here, where we can see that the 4 parameters that are available for performing and hear how they behave. On tones like this, it's much easier to hear the stepping that is happening across these parameter combinations. So as we move this parameter, we can hear the discrete steps at which the parameters were set and the samples were recorded. On certain sound slices, it's easier to hear how the 1 second of audio is being looped with slight crossfades. At some point in the future, it might be nice to find ways of stochastically playing back the sound slice to avoid this looping sound. But overall, as a user turns these knobs, there's a satisfying sonic result that hopefully emulates the use of turning a physical knob on a synthesizer. The second way of interacting with these sound slices is through the 3-dimensional plot that is provided in the second window that you saw. The 3 dimensions here are the x-axis, the y-axis, and then color, which is available to represent a 3rd dimension of the data. The way that we created this plot was we took the 50,000 data points that are in the 357-dimensional space. We first standardized that data set to make sure that all of the ranges of the different dimensions were relatively similar and therefore would be relatively equally weighted in the distance measures that our data analysis would do further down the pipeline. We then used principal component analysis to reduce the number of dimensions. We set the PCA algorithm to maintain about 95% of the variance, and this often reduced the number of dimensions down to around 200 or so. So reducing the data set quite significantly, but retaining the salient aspects of it. Next, we used uniform manifold approximation and projection to reduce the remaining principal components down to just 2 dimensions for plotting as the x and y positions on this plot. We chose not to use UMAP to reduce to 3 dimensions and have a 3rd dimension be color, because in my experience I've often found that using color as a 3rd dimension of a UMAP or other dimensionality reduction algorithms doesn't turn out to be as perceptually useful as we might think. As we'll see in a moment, the user can of course move their mouse around in this 2-dimensional space and browse the different sound slices that are represented here as data points. Additionally, each one of the axes, the x-axis, the y-axis, and the color dimension, can represent any one of these 7 different analyses, either of the 2 dimensions that UMAP provided, but also the mean pitch confidence, mean loudness, mean spectral centroid, or mean spectral flatness of the sound slices themselves. And this is selected from the original audio analysis that we did on all of the sound slices. I can now change the x-axis to spectral centroid and the y-axis to loudness. Or the x-axis to pitch and the y-axis to spectral flatness. And the color can change to any of these as well. In order to give the user a little more control over how they might be navigating these sounds and use them musically and performatively, we decided to also provide an emulation of the touch-activated keyboard sequencer that's found on the original Serge Modular. The user is able to store up to 16 slice presets, 16 data points that they find in the plot or in the parameter combinations, by simply pushing the save button and then choosing which step they want to store it in. And this is important because as the user is using SMAI, they might want to return to a particular sound that they've found, and trying to return to that exact position either with the parameter combinations or on the plot would be rather difficult. Additionally, rather than trying to build into SMAI modulation parameters such as LFOs, we decided to open up all of the control parameters of SMAI to both MIDI control and OSC control, and this includes the 4 knobs on the skeuomorph, the X and Y position on the plot, which axes the X, Y, and color axes will display, advancing the step sequencer, and jumping to a particular step in the step sequencer. So the user can use these control parameters to build a performance instrument, more carefully navigate the data set, or do more complex sequencing in a DAW. As I said, the audio analysis and statistical analysis was done in SuperCollider with the Flucoma toolkit. Additionally, the standardization, PCA, and UMAP was also done in SuperCollider with the Flucoma toolkit. And the app itself was built in C++ using open frameworks. All of the code in SMAI, including the C++ code and the SuperCollider code, is licensed under the BSD 3-clause license, and all of the audio files that were recorded and analyzed are licensed under the Creative Commons 4.0 International license. In the future, we're looking to find more users who can join us in using this instrument, find more ways of using it musically and expressively. In particular, we're interested in exploring the different choices that are made as part of the musical analysis and the dimensionality reduction tools that we used. So how might these plots and instrument feel different and be musically different if we chose different audio analyses or different statistical representations of those audio analyses, or if we used different dimensionality reduction techniques? How might that change the way that the instrument feels and how it can be used musically, and what it can tell us about the audio and the data that we've analyzed? Also, we're interested to add more analog hardware synthesizers to this project. Aside from the Serge Modular Skeuomorph portion of SMAI, the audio analysis, data pipeline, and three-dimensional plot could easily be applied to other vintage analog synthesizers, and it would be fascinating to see how they compare or how they would also fit into a system like this. And of course, we're looking for more coders to join the project and support it and help it grow. Thank you for listening, and please join us at this GitHub repo where you can download and perform with SMAI, as well as learn more about it and contribute to the project.